Welcome to the Problems Channel Season 3, Episode 25, the episode which I titled A Divisibility-by-7 Algorithm, because in this episode we will discuss a design process of an algorithm that can be used to detect whether a given positive number is divisible by 7 or not, using the scope reduction or the so-called reduce and conquer problem solving approach. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, especially after the season number 2, first of all, thank you very much for your vote of confidence. Thank you for joining our channel, and thank you for subscribing to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel, who we are and what we do. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current supporters and the current subscribers of our channel. The objective of the mathematical problem S3E25 is to design an algorithm or a test that can be used in order to detect if a given input whole positive number is divisible by 7 or not. And as a hint, that design process should follow the template of the scope reduction or the so-called transform and conquer problem solving approach. For those of our viewers who joined our channel after season 2, we recommend that you watch season 2 episodes 21, 22, 23, and 24, because these are the episodes in which we studied the scope reduction or the reduce and conquer problem solving approach in a dedicated manner. As such, I will not be deep diving into explaining how this problem solving approach works. I will just say a few words that in a lightning round, the overall objective of applying the scope reduction or the reduce and conquer problem solving approach to the process of generating a solution of a given technical problem is the following. First, we want to reduce the current difficult to solve problem to another problem that is smaller and simpler in some sense. That's number one. Number two, during that reduction process, we want to preserve the DNA or the technical essence of the original problem, because the overall end goal of this recursive reduce process is to arrive at a state in which we either solve the original problem, in other words, at the end of this reduction chain, there sits actually a solution of the given problem, or at least if we cannot solve the problem entirely, we gain enough of technical and tactical advantage in order to unwind our steps back in reverse order and climb back up and solve the original difficult to solve problem. In one of the episodes that you see on the upper right hand side of your screen, we actually studied how the Euclidean greatest common divisor algorithm works, because that algorithm is a wonderful representation of how the scope reduction or the reduce and conquer problem solving approach works. We will begin our design process with an observation that cannot be qualified in any other way than childish. And quite often when students see the first step in any solution of any technical problem, they think that a joke is being played on them. So the number 7 is representable as 10 minus 3 as the difference between 10 and 3. And this observation is so important that I even carried it out into the thumbnail of this episode. If you care to look at the thumbnail of this episode, at the very top centered, you will see this particular observation. Now, this is not a joke, but this is what I call an Eulerian observation, because the Swiss-born mathematician and theoretical physicist Leonhard Euler was a master craftsman of first making or starting with an observation that cannot be qualified in any other way other than childish, but then spinning this seemingly childish observation creatively 7 ways to Sunday into something that is not trivial at all. So if you want to make any progress in mathematics, theoretical physics, or computer science for that matter, I highly recommend that you read the works by Leonhard Euler. He was, like I said, a true master of pulling these kind of stunts when he will put down on paper in black and white something that seems to be trivial, but then creativity, his technical creativity will take over, and voila, several pages later, there is a wonderful, interesting result that, you're right, you guessed it, it carries the name of Leonhard Euler. So here is a childish Eulerian observation. 7 is equal to 10 minus 3. How can we use this to our advantage? How can we spin this Eulerian observation creatively into something that is non-trivial and design a divisibility by 7 algorithm? Well, here's one way. We replace 10 with x, 3 we replace with a, and now we have an expression that looks like x minus a. Now, since we're dealing with divisibility, what does this formation remind you now? Well, if you go back to your basic and rudimentary theory of polynomials, you would recall that this here special type of a polynomial called a binomial divides a certain polynomial or certain shape. Like, what is the advantageous shape of such a polynomial that this binomial should divide that will help us design a divisibility by 7 algorithm? What can you say? Well, remember that any whole positive number can have multiple types of decompositions. For example, a whole positive number can be decomposed over primes. But prime factorization of especially large numbers is a challenge of its own, so we do not really want to deal with it right now. But in another type of a decomposition, a whole positive number can be decomposed over a certain base, b. And a popular base is base 10. So in base 10, let's say our favorite number represented in base 10 can be written which way? It will be a sum of coefficients ak times 10 raised to the kth power, where k varies from 0 to m, and the alphabet of the coefficients ak in this case comes from where? The ak belongs to a set of numbers that run 0, 1, 2, 3, so on, and 9. This is the alphabet for the base 10. These numbers run from 0 to b minus 1. b is equal to 10, so the numbers run 0 through 9. So this is, you can see, this is one number already raised to a certain power. And this may give you an idea to recall that according to the polynomial remainder theorem, the binomial x minus a divides the polynomial, let's say, p of x, if and only if a is a root of polynomial p of x. In other words, when a is substituted into our polynomial, we get an identical 0. So what is the shape of the polynomial that is advantageous to us in this case? Well, again, this decomposition of a given number over base 10 should give you enough of a hint if you recall this childish observation. The shape of the polynomial should really be p of x is x raised to the power of k minus a raised to the power of k. This shape of the polynomial is especially advantageous. Why? look over here, k varies over some number of interesting digits in a given number. And that means that this number over here flip-flops through what? Even odd, even odd, even odd. And this polynomial over here is divisible by this polynomial over here for all parities of k, whether k is odd or even, it doesn't really matter. The binomial x minus a always divides this here polynomial. And in our particular case, we also understand that the binomial x minus a will divide the polynomial x to the power of k minus 3 to the power of k. See, here we're going in the opposite direction from a to k and from x to 10. 3 minus k, and for that matter 10 raised to the power of k minus 3 raised to the power of k. And now that you honed in on this type of a polynomial, what will be the next step in the design of the algorithm? Well, the next step will be to propose the decomposition of our number in pseudo base 3. I will maybe even mark it with the 3 prime over here, where we decompose the given number over the same coefficients. That is the key. The same coefficients that are represented in the base 10, genuine base 10 decomposition of the given number, go into the pseudo base 3 decomposition of that number. But here we multiply these coefficients, the very same coefficients that sit in the base 10 representation of our number. We put them over here, but we multiply them not by the base 10, but by the pseudo base 3. 3 raised to the power of k. K varies over the same range. And now what do? Well, the shape of the polynomial, 1, 2, 3, we have this. So now from here it follows that we construct the difference, delta, that is n10 minus t3 prime, which will be what? It will be our coefficients a, k, which are the same in both cases, because that is how we constructed our pseudo base 3 decomposition of the given number, where k varies from 0 to m. But here we will have what? Here we'll have times this specific number. You see, this number will be represented in this here delta. And we just showed that this number is always divisible by this number. But this number is what? Oh, looky look, it's 7. So our delta is always divisible by 7. And because this is a finite sum, the if you will, the apparatus of modular arithmetic takes over. If each and every term that carries this number is divisible by 7, then the entire sum is divisible by 7. We will have only one left over. The coefficient in the decomposition of both cases, it will be something, 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 a0. It could be any number from this here alphabet, and we will have the same decomposition in this case. It will also be a0. But the trick is that when we construct the difference, we erase this free floating term and we come only to the terms that carry this difference over here. And that means that this difference is always divisible by 7. And here is the wonderful conclusion. Using nothing but the elementary or basic arithmetic of middle school level and not more, it can be shown that if we have our delta always divisible by 7, in other words, 7 always divides delta, that means that the fates of the divisibility of the numbers n10 and t3 prime by 7 are decided in parallel. And here is our algorithm. That means that if number n10 is or is not divisible by 7, then the number t3 prime is or is not divisible by 7, and the other way around. If the number t3 prime is or is not divisible by 7, then the number n10 is or is not divisible by 7. And what does it mean? Well, this number over here, let's put it this way, number 10, in general, it will be smaller, the number t3 prime will be smaller than the original difficult to solve problem. And that is how we capture the heart and soul, or the technical essence, of the scope reduction or reduce and conquer problem solving approach. Instead of fighting the fight with the difficult to solve problem, we fight the fight with its smaller representative, because, as we just showed, the number T3 prime carries the technical DNA of the number, and 10, in other words, the divisibility of the number T3 prime is exactly the same as the divisibility property of the original number n10. And once we make this realization, we recursively promote the number T3 prime, whatever it comes down to be over here, genuinely usually smaller than the original number. We promote this number to be, again, number that is written down n prime in base 10, and then we decompose it by the same rule. And thus we shrink every time, on every iteration, we shrink the size of the problem until, so this number, we come up with a number that is smaller, another number that is smaller, and another number that is smaller, and so on, until we arrive at a number that will be what? It will be either 7, we wonder, or we think, or it will be a number from which set? Well, it could be 6, 5, 4, 3, 2, or 1. One of these numbers. So it's 7 versus the number, any number from this here set. And what does that mean? That means that our algorithm is designed and we are done. We started with a childish or an Eulerian observation. We creatively brought in the parameterization of this childish observation, brought in the polynomial remainder theorem, constructed the useful polynomial, constructed the base 10 decomposition of the given number, the decomposition of the same number in pseudo base 3, took their difference, showed that this difference is always divisible by 7. That means the conclusion that we made, and voila, our design is over. If at the end of our reductive chain, or the chain of steps where we reduce the number into pseudo base 3 all the way through, winds up being equal to 7, then the original number is divisible by 7. And if at the end of this chain there sits a number from this set, 6, 5, 4, 3, 2, 1, then the original number is not divisible by 7, and the game is over. Now that you understand how this theory works and how the design process of this algorithm unfolded, let us see how this algorithm will work in practice. Wonderful. Now let us apply the theory that we just developed a few seconds ago to this here sample number. We'll refer to this number as N10, 5,523, for example. That number, as we already seen in the previous segment, can be decomposed over the base 10 as follows. The first coefficient will be 5 times 10 to the third power plus 5 times 10 to the second plus 2 times 10 to the first power plus what? 3. Now we construct the number to which we refer as T3 prime pseudo base 3 decomposition. It's the same number, 5,523. We'll put it in double quotes because this is the number that is based on this decomposition, this number right here. So this comes down. We carry down, remember, we carry down the coefficients. So it will be 5. We already know 5. It will be 2. And it will be 3 in this case, but we will multiply these numbers by what? I will even use the different chalk, the different base, pseudo base. 3 and 3, and here we will have 3 cubed plus 3 squared plus 3 to the first plus. Now we compute what the real number in this decomposition comes out. If this is confusing, then let me perhaps maybe even erase it. Now that you understand how these things work, we will just use it like so. 3 cubed is 27. 27 times 5 is what? 135. 135 plus 45 is 180. 180 plus 6, 186. 186 plus 3 will be 100. Well, let's do it this way. 189. This is our T3 prime, 189. And look at this. Most definitely we have 189 is less than 5,523. This is the essence. We managed to reduce the size and or complexity of the original problem, but the divisibility by 7 DNA of the original number is preserved in that number. In other words, the fate of the divisibility of this here number is decided by the fate of the divisibility of this smaller number. Now we repeat this process again. We now promote this number to be represented in base 10. So we have n prime 10 is equal to 189, which is representable as what? 1 times 10 raised to the second power plus 8 times 10 raised to the first power plus 9. And now we have our t prime 3 prime, which is what? Will be some number. We will compute. Let's write it down over here. 1, 8, 9 plus this will be the second power, this will be the first power times. At this point you already should be telling me this is number 3. This is our pseudo base 3. So 9 plus 9 is 18. 18 plus 24 comes out to 42. So this number is 42. Let's write it down over here, 42. Let's pretend that 42 is still the number that is large, for example. But notice this, that so far we have the following chain. Let's write it down over here. We will see where this chain will take us. 5,500, what was it, 23 is larger than 189, and this is still larger than 42. Let's apply the same maneuver to the number 42. So we have another number in base 10, which is 42, and that is representable as 4 times 10 to the first power plus 2. And now we have our t prime prime 3 prime, the pseudo base 3 decomposition. The coefficients are the same. We carry them down mechanically. We do not even think. Something to the first power plus, well, in this case it will be 2. Doesn't really matter. So what do we have here? 3 raised to the first power. 12 and 2 is 14. So this is our 14. 14 is still a large number. We still did not whittle it down. We keep rolling, but we record that this number is still here. Look at this. 14. We're still rolling. So the number n prime 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 10, 14 decomposed over 10 as follows. 1 times 10 to the first power plus 4, and our pseudo base 3 decomposition of the same number comes out to what? 1 times something to the first plus 4. This is again base 3, the pseudo base 3. 1 times 3 to the first 3 plus 4 is 7. Look at this. At the end of our reductive process, there sits the number 7. So the question is, what was it? 14, and now we came down that is greater than 7. So the remainder of this process is this here number. So the question is does 7 divide the result of this process? Yes, it does. So since 7 divides 7, it follows that 7 divides 5,523. It pays for you to understand again how this reductive process works on your own. Come up with any number that you like and see if you can decompose this number into base 10, then in pseudo base 3, and roll it down all the way to the final result when you cannot decompose the number anymore. 7 is representable as just 7, even in base 3, and the result that you obtain will decide the divisibility of the result by 7 will decide the fate of the divisibility of your number by 7. Now that we looked at the situation where the input number is divisible by 7, let us examine the case where the input number is not divisible by 7. To that end, without getting too fancy, we take a number that we know ahead of time will not be divisible by 7, but in order to see how the mechanics of our reduce and conquer problem solving approach applied to this problem unfold by ourselves, in order to make sure that our brain bone to hand bone connection is active, we grab a pen, piece of paper, and we roll through the computation ourselves. The input number is 5,521. Its base 10 decomposition will vary from the previous one only in the unit section. It will be +1, not +2. The corresponding pseudo base 3 decomposition will also be different only by 1. In the end, we will have the number 187, and interpreted in base 10, its decomposition will also vary. In the unit section will be +7, not +9. In the pseudo base 3 decomposition, +7. Obviously, the result will change. 9 plus 24 is 33. 33 plus 7 is 40. We decompose 40 over base 10 as 4 times 10 to the first plus 0. And carrying down the coefficients, we have the following pseudo base 3 number. It will be 12. 4 times 3 plus 0. 4 times 3 is 12. 12 plus 0 is 12. And lastly, 12 is replaced with technically what? With the number 5. 1 times 10 to the first plus 2 is 12. Carrying down the coefficients, we have 1 times 3 to the first plus 2 is 5. So in some sense, we basically, as you can see already, we reduce the result modulo 7, because 12 is representable as what? 1 times 7 plus 5. 5 is less than 7, and boom, voila, we have our result. At the end of the reduce and conquer or scope reduction chain of consecutive reductions of the problem that is difficult to solve, and the replacement of this original large difficult to solve problem with smaller and smaller copies of itself that does carry the DNA, the technical DNA of the original, we arrive at the number 5. The question is, does 7 divide 5? No, over the arithmetic of integers or in integral division, 7 does not divide 5. Consequently, 7 does not divide 5,521. And if you play enough, so here we have the result that was carried out into the title of this segment. No cigar. 5,521 is not divisible by 7. And once you play with this algorithm long enough, then you should be able to observe that we have an opportunity for a slight modification or for a slight improvement of our algorithm that will make it more mental only computation friendly. Before we adjust our divisibility by 7 algorithm to make it more mental only arithmetic friendly, I would like it to make official and say that mental arithmetic has absolutely nothing to do with mathematics. Most mathematicians are not good at mental arithmetics. Most mathematicians do not like mental arithmetic because, again, mental arithmetic has nothing to do with mathematics, and some mathematicians actually go as far as despising the numbers to begin with, because an insane amount of mathematics can be done without the numbers of any kind, but that is a separate issue. So why do we want to adjust our divisibility by 7 algorithm to make it mental only arithmetic friendly? We want to do that because, remember, mathematics is an art of telling a story of how and why, and in order to adjust our divisibility by 7 algorithm to make it more mental only arithmetic friendly, we have to do precisely that. We have to use our technical ingenuity, creativity, tell a story, come up with an improvement, and once we do, we pretty much lose all the interest to it. Again, this channel has nothing to do with me. My personality is absolutely irrelevant, but I have much more fun designing and inventing these things, and once I do, I sort of lose all the interest in actually using these results in practice. But let us see what we can do over here. Our decomposition of the input number over genuine base 10 or fake or pseudo base 3 can be parenthesized by factoring out the base or the pseudo base out as many times as possible. This factoring out results in the parenthesization, and if we torture this parenthesis enough, we can even predict and compute how many parentheses will be there. But the idea here is that this parenthesization of our decomposition of the input number lends itself naturally to the verbalization or a verbal description of our algorithm, which is what? Processing input number left to right, as shown with the red arrow over here. We work two leftmost digits at a time. That is, multiply the leftmost digit by the current base or pseudo base, let's say by 3, and add the next number. Then multiply this result by 3, add the next digit. Multiply the whole thing by 3, add the next digit. So here, this process is shown with the either the genuine base 10 or a pseudo base 3. And here on this line specifically, I wrote it down for you how we can carry out this conversion in our head only or mentally only. Leftmost digit 5 times 3 is 15 plus next digit 20. 20 times 3 is 60 plus next digit 62 times 3, 186, 186 plus 3, 189. Boom. Pretty much in our mind, in a reasonably comfortable manner, we process the input number left to right, one digit at a time, times the pseudo base plus the next digit times the pseudo base plus the next digit, and so on. This is our number. But here is the improvement. This is where we think like a mathematician, where we put our mind into a mode that is isomorphic to the mode in which the mind of a practicing mathematician operates, when that mathematician operates in his or her professional capacity. So before we add the next digit processing the digits of the input number left to right, we reduce the result modulo 7. In other words, if we designate the digits of our input number left to right, A, B, C, D, and so on, when we multiply A by 3, instead of working with the actual result, or naked result, if you will, we reduce this result modulo 7. In other words, we cast out as many copies of 7 as possible before we step into the negative whole numbers land, and we come up with a number that is between what? Between 0 and 6. 0, 1, 2, 3, 4, 5, and 6, which actually is set, forms a nice group under a certain operation. Think about which one. So here, let's do our modified algorithm on the input number 5523. Working on this number left to right, two leftmost digits at a time, we go 5 times 3 is 15, reduce modulo 7 is 1, 1 plus 5 is 6. So now we grab this number that is result of these two steps, and we replace these two digits with the result. So the number 5523 is replaced with an isomorphic modulo 7 image called 623. Now we process this reduced number. Remember, reduce and conquer, scope reduction. Reduced number by value the same way. The leftmost two digits. 6 times 3 is 18. 18 reduced modulo 7 is 4, because 2 times 7 is 14. 14 plus 4 is 18. 4 plus 2 is 6. So now our number 623 is reduced with its isomorphic mod 7 image, 63. Okay, we already know 63 is too small, already small enough. We can multiply 7 by 9 and conclude this number is divisible by 7, but let's run down our algorithm anyway. 6 times 3 is 18, reduced by modulo 7 becomes 4, 4 plus 3 is 7, boom, that's it, no more digits. All the two leftmost digits, all the material exhausted, no more material, 7. And our number is divisible by 7, because 7 divides 7, hence 7 divides 5523, or the other way around, 5523 is divisible by 7. Now let's do this, and this arithmetic can be carried out without pen and paper, in one's mind only, if we just stare at that number and run through this very straightforward algorithm. For example, let's apply this algorithm to this here number that is large enough, 48,893. Is this number divisible by 7 or not? Yes or no, with absolute certainty, and why? Well, we stare at that number and we crunch through our algorithm in an expedient manner. Again, left to right, two digits at a time. 4 times 3 is 12. Reduced modulo 7 becomes 5. 5 plus 8 becomes 13. So our number 48,893 is taken into 13,893. And now to that number, recursively, we apply the same steps. Let's write it down over here. 1 times 3 becomes 3. Reduce modulo 7, it becomes 3. 3 plus 3 becomes 6. So our number 13,893 is taken into 6,893. Again, we process that reduced number, 2 leftmost digits at a time. 6 times 3 becomes 18. Reduce modulo 7, it becomes what? 4. 4 plus 8. 4 plus 8 becomes 12. So our number is 68 replaced by 12, and then the last 2 digits over here, 1,293. Let's write it down, 1,293. Again, processing that number left to right, 2 digits at a time. We have 1 times 3 becomes 3. Reduce modulo 7 is still 3. 3 plus 2 is equal to 5. So number 1,293 becomes 593. Wonderful. Processing this number 2 leftmost digits at a time, left to right. This way we compute. 5 times 3 is 15. Reduce modulo 7 is 1. 1 plus 9 becomes 10. So our number becomes 103. Wonderful. Processing that number left to right, 2 leftmost digits at a time. 1 times 3 becomes 3. Reduce modulo 7 is still 3. 3 plus 0 becomes 3. So our number is taken into 33. Wonderful. Last 2 digits, so we crunch them. 3 times 3 becomes 9. Reduce modulo 7 is 2. 2 plus 3 is 5. Look at that. 5. Does 7 divide 5? No, 7 does not. 7 does not divide 5. Hence, 7 does not divide the number 48,893. The other way around. 48,893 is not divisible by 7. Now, if you are into mental arithmetic, have fun, but my claim is that our improved algorithm is actually mental-only arithmetic friendly, because here we do not have to do very complicated arithmetic at all. We have to multiply any digit that can be in the range from 1, actually, in a meaningful way, or if you want 0, 0 to 9 by 3, that much we can handle. Reducing modulo 7, this apparently at most 2-digit numbers is also mental-only arithmetic friendly. Adding, so replacing, and probably the most difficult part over here is to see where you're replacing the leftmost 2 digits with. So that's probably just about the only challenge, but this is what we have. This is an improved, if you will, algorithm. And if you understood how we designed this specific algorithm, then you should be able to come up with other like algorithms that are based on the scope reduction or reduce and conquer problem solving approach, the essence of which is to always come up with the number that is smaller than the original. Look at this. 13,000 is less than 48,000. 6,000 is less than 13,000. 1,000 is less than 6,000. And then we whittle it down. 1,200, 593, 103, 33, and then boom, 5. And if my gut is telling me, if my gut is on the money, then it looks like with this here algorithm, actually what we produce by the looks of it is the remainder of the division of that number by 7. So this is the essence of this algorithm: smaller, 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 smaller number, but each reduced number carries the divisibility by 7 DNA of the original. You see, and again, here is another thought. I'll give it for you as an exercise. Here we look at this. We engaged in a process that was reductive. Every time through this step, we came up with a number that was smaller, smaller, smaller and smaller. But you're already a smart bear, you know what's going on. Once we came here to the number 5, we think that some processes may be reversible. So in other words, if we shoot this as a movie, we can run this movie in the reverse order. So from number 5, we can actually climb the way back up this way, make 5 larger. 5 into 33, 33 into 103, 103 into 593, 593 into 1293, and on and on and on. And then the question is, who is there to tell us that this is the number? Well, this number came, this is just an intermediate step of another larger number, and yet a larger number, and so on. We can work this in reverse order and bump up this number to create more and more larger and in some sense more difficult problems. But now this is it for the mathematical problem S3E25, and we will move on to a new challenge next. Our next challenge will be a problem in theoretical physics. We will call it Season 3 Physics Problem number 6, if I'm not mistaken. And the challenge is, this problem is the following. We're given a line segment of length r, and a line segment is taken to be a body that is rigid. In other words, at any time when this line segment is executing any sort of motion, the distance between any 2 points taken on that line segment remains one and the same at all times. So a line segment of length r, let's say in near Earth gravity, executes the following 2 motions at the same time. First, it descends in the, let's say, uniform Earth gravity from certain height towards the Earth's surface at a constant velocity v by direction, in direction. That means technically the center of mass, but this is a uniformly, let's say, massive line segment. It falls down in the near Earth gravity, in uniform gravity, with the same velocity v. It is an artificial, of course, thought experiment, but that's what it is. It's descending with the constant velocity v. That's motion number 1. Motion number 2, at the same time as, let's see, at the same time as our line segment descends in the uniform Earth gravity with constant velocity v, it also rotates in the horizontal plane with the constant angular velocity omega. Constant angular velocity omega in the horizontal plane in such a way that it rotates about one of its extremities. In other words, when it comes to the rotation, forget about the descent in the uniform Earth gravity with constant velocity. Let's say we froze that motion and we only consider the rotational motion. Then it rotates about one of its extremities. So the further the other extremity rotates in the horizontal plane, or in this direction, it doesn't really matter, by that distance r. That distance. So let's say this point is rotating. So the question is this: given these 2 conditions, uniform the descent of our line segment in the uniform Earth gravity with constant velocity v, and its uniform rotation in the horizontal plane about one of its extremities, let's say this one, it rotates this way or that way, doesn't really matter. We want to find the following things. First of all, we want to recover the shape of the trajectory of the point, let's say B. Let's say this is the point A. So with respect to the point A, the line segment rotates. This is the point B. So the point B, which trajectory does the point B trace in space? This time it will be obviously like before. So far we worked with planar curves. Now we're stepping out from 2D into 3D, from a plane to 3 space. So we want to recover the shape of the trajectory of the point B. In other words, as this point right here rotates about this point right here, and it also descends and rotates, what is the shape of the trajectory? Then we want to find the second parameter. We want to find, let's say this will be the round v, or let's say it will be v0 and omega 0. We will use the zeros index in order to underscore the fact. Usually with some specific numbers in physics, we designate the quantities that are constant, that do not vary in time. The angular velocity doesn't vary in time, and the linear velocity of descent does not vary over time. So we want to find the velocity v of the point B, and obviously would be nice to have it as a function of time. We also want to find the acceleration of the point B as the function of time, and another thing that we want to find is the curvature of B's trajectory. And here we take it that the numbers v0 and omega 0 are given to us, so all the answers that you will obtain, they are expected to carry these two numbers, and of course t is a parameter, and all these functions that we see over here should be, in theory, within the functions of time. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the theoretical physics problem S3E25.